Good evening, everybody. Wow, that's an interesting. We got some echo here. There we go. Thank you, Thomas. Good evening, everybody, and welcome to the Hubble Space Telescope Public Lecture Series. I'm your host, Dr. Frank Summers of the Office of Public Outreach, and it is my pleasure to be your host every month, and also to give away free pictures. We have a brand new lithograph. This has never been given out before at the Public Lecture Series. You know, those of you who've been here many times say, oh, it's another galaxy picture that I've got. Well, this one is one you haven't got. It's a galaxy cluster Abell 2744, a very special galaxy cluster because it is the first cluster in the Frontier Fields project. Okay, and so you get the picture of this galaxy cluster. It's special because it is a very, very large galaxy cluster. It produces gravitational lensing, all right, which helps us to see very distant galaxies that are magnified by the gravitational lens. You want to learn about that idea. We've got information on the back that you can read about. There's at least a couple left. If you did not get one on the way in, please pick one up on the way out. Our talk tonight by Marc Kamionkowski, which I spelled wrong, obviously. Kamionkowski. Sorry about that, Mark. A telegram from the early universe. Okay, upcoming next month, Joshua Peak will be talking about outer space. Basically talking about the emptiness that's out there and what's actually in the space between the stars. It's not really as empty as you may think. January, this auditorium is going to undergo some renovations. Okay, there will be some renovations, and so the first week in January, I was told I could not hold the public lecture series. So we are holding it on the second Tuesday in January. So January 13th, 2015, and it will be a fascinating topic by some amazing astronomer. Basically, the astronomer to be named later. That don't worry, I get there. Okay, it's been a little busy this month, but we'll get there. In February, we have one of the longer titles of topics that have been given to me, From Cosmic Birth to Living Earth, the Next Great Space Telescope Beyond JWST. If you come to these, you know we've talked a lot about the next great observatory, the James Webb Space Telescope. For those of you who are wondering what's beyond even that, Jason Tomlinson will elucidate you in February of next year. Okay, these are listed on our website. Easiest thing to do is just say Hubble Public Talks into your favorite search engine. This should come up. You can see we've got the upcoming lectures as well as the archive back to 2005. So that's 9 years of amazing cosmic knowledge that you can absorb by watching all of our webcasts. Okay, just think how smart you would be watching 9 years of cosmic knowledge. Anyway, so that's available for you. We have emails. I just got one tonight of somebody who was on our email list and for some reason got off of it. So she gave me her email address. I'll add her. You won't get any spam from it because it's very, very low emails. You can contact us, publiclecture@stsci.edu, ask us comments, questions, or even sign up for the announcements, because if you send us an email, we'll have your return address to do it. Social media, Facebook, Twitter, Google+, Pinterest. I'm on Facebook, Google+, and sometimes I Twitter. I don't do as much of the social media as I'm supposed to, but it's there if you are so interested in it. Observatory. I'm not sure that they are doing the observatory tonight because they had it scheduled for last week, and so there's a big question mark. Anybody from the Space Grant Observatory here? Hearing silence, I will assume that they are not going to do the observatory tonight. Remind me to ask again at the end of the lecture in case the Maryland Space Grant Observatory folks do show up. Okay, so my favorite part of the evening is the news from the universe. This is for November 2014. To Pluto and beyond, part 2. When last we discussed, of course, when we're talking about going to Pluto, we are talking about the New Horizons mission. New Horizons launched back in 2006. It went past Jupiter in 2007, has been cruising out towards Pluto for the past 9 years, and will finally get to Pluto next summer. So here is the path of the New Horizons full trajectory as it was in July when I first presented part 1 of this. And part 1, and just to mention the milestones, sometime January or shortly thereafter, New Horizons will have better resolution than Hubble does. Okay, so all of next year, the time for New Horizons is precious because they will have better resolution than Hubble. These are some Hubble images of Pluto where you can see the pixelation of it. All right, and that's the best Hubble can do in terms of getting individual pictures. We can, of course, interpolate from them to get better maps. But next summer, for next year, we'll be able to get that. It'll go past Pluto on July 14th, Bastille Day next summer. We'll do a buzz over Pluto. It will be moving, however, really, really, really fast. So this is going to be a very carefully planned encounter of everything. And Hubble has been helping by searching through the Pluto system, discovering the moons Nix, Hydra, Styx, and Kerberos, the 4 extra moons of Pluto that Hubble has been able to think. But after it passes by Pluto, what next? Well, this is where the Kuiper Belt comes in, and you can see that what we have here in the interior is the orbits of Jupiter, Saturn, Uranus, and Neptune, the giant planets in the solar system. All of those white and red objects are new objects that have been discovered in the Kuiper Belt of the solar system since 1993. Well, I say all of them but one. Of course, Pluto was discovered in 1930. There are 1,274 as of July this summer. And so the question is, we're going to zoom past Pluto. What do we do afterwards? Can we find a suitable Kuiper Belt object to fly past afterwards? So Hubble showed that it could do it, and NASA gave us the go-ahead to do a complete search for Kuiper Belt objects that would be obtainable with the current orbit of the mission. So they looked at 83 Hubble WIF-C3 fields, okay? And this is the tile mosaic of all these 83 fields that they looked in. And on the lower left-hand corner is the size of the full moon on the sky. And so you can see that they covered an area about half the size of the full moon in total, looking for potential Kuiper Belt objects that the New Horizons mission could visit. They discovered 3 that were really obtainable potential targets. Right? And so if you take those blue as the WIF-C3 fields, and then the purple as a single WIF-C3 field, and then you zoom into that red region, you can see how just a small piece of that they had to do. And you can see the 5 separate images are different exposures. You take multiple exposures separated by time, and then the nearby objects, the object in our solar system, will move across the exposure, creating those 5 separate images. So here is what they called PT1, Potential Target 1. You can see its real name is 1110113Y, which is why we call it PT1. And this is one of the this is the favored target for New Horizons to mission to visit after going past Pluto. So as I said, there are 3 potential targets. The size estimates for these are between 25 and 55 kilometers. One of them is definitely reachable, and when we say definitely reachable, the idea is that we need enough propulsion to shift the orbit, to shift the path of New Horizons to go past this object, right? And so given the constraints of the propellant and stuff we have on board, can we shift it? And so one is definitely reachable, 2 of them are potentially accessible, but just because we found potential targets doesn't mean that New Horizons is actually going to go there. NASA has to approve and fund the extension of the mission. The mission is funded through the Pluto flyby and all of the analysis of that data. NASA must approve the funding for that. So they're going to go through the entire year next year, and somewhere around in early 2016, the decision will be made whether or not they're going to go and look at a second object.
There's no worry that
No worries of a collision. The question was, no, it's pretty, really totally empty out there. I mean, well, you're used to, if you saw Star Wars, you know how dense the asteroid belt isn't, because there's spaceships zooming through the asteroid belt is pure fiction, okay? If you fly through the asteroid belt, you will never, ever know that you're inside the asteroid belt, because it's just incredible amounts of space in between the asteroids, okay? Same thing, even more true for the Kuiper Belt objects, okay? Incredible amounts of space in between them. So you have to work really, really, really hard in order to fly past one of these, okay? Here is just for example, the potential target 1, 30 to 45 kilometers in diameter, compared to asteroid Eros that we flew past, and rubber ducky, also known as Comet Churyumov-Gerasimenko. This is the Rosetta target, which is only 4 kilometers in diameter. And of course, rubber ducky is going to get visited, is currently being visited, but it'll have a lander tomorrow. We had a question there?
Yeah, how much further out are these new targets?
Getting there in just a second, okay? Good question. How much further away is it? Well, so here is an artist's depiction of it. And so this is the idea of what it might look like, this Kuiper Belt object way out at the edge of space. And the idea is that it's supposed to be here, but this is, of course, fantasy. This is not even scientifically correct. It's a nice idea, but you recognize when I showed you that path that New Horizons that has been going straight past Pluto, and Pluto is about 3 billion miles out from the sun, and this new object is about 4 billion miles out. So the problem with this diagram is that that object should be moved over to the end of that green line. And actually, if you're looking back at the sun from that object, you should be seeing Pluto in a direct line with the sun, because New Horizons is not going to be able to change its path very much. So it's all right. It's just an artist's rendition here. But the point is that it's about 4 billion miles out. So after traveling 3 billion miles over a course of 10 years, it's going to have to travel another billion miles to get there, which will take another 3 or 4 years to get there, okay? Which is the question I think you were really asking, right? Right, okay. Okay, next topic, a close encounter of the fourth planet kind. This is another revisit of a story that we've been following. Of course, comet Siding Spring. Siding Spring, which flew past Mars last month. This is a Damien Peach. God, the guy gets amazingly good comet pictures. Damien Peach. This is a picture of comet Siding Springs from February of last year. And of course, in October, it flew past Mars. And it's on this giant looping orbit. It's got like a 1,000,000-year orbit, okay? And it's coming down underneath the solar system and back up through it, and it just happens to pass by the orbit of Mars, and Mars just happened to be there at the same time it was passing by. Incredible coincidence. This doesn't do it justice. It actually came within 20 Mars diameters of Mars on there. And so, of course, there's going to be, on the scale of the solar system, that's amazingly close. All right, so we're wondering, was there going to be any problems? This is an artist's depiction of the comet flying past Mars, and this was to illustrate the idea that NASA was going to do a duck and cover. Take the 3 spacecraft that we have in orbit around Mars and make sure they were on the far side of the planet at the proper time so that they wouldn't get hit. But this was overly optimistic in terms of the size of the coma of the spacecraft, of the comet. It wasn't nearly that big. There wasn't any huge problems with it, and after the flyby, they put up this webpage saying everything's in good health. MRO, Maven, and Odyssey are all in good health. No problems there. Wasn't really something we were sweating amazingly, but you know, if the coma had been really, really big, there could have been some serious problems. What we were interested also in is the ones on the surface. Could they look up and see an observation of a comet from another planet? First observation of a comet from another planet, and they got it. It's not that impressive, but they did get it, okay? So that in the center is comet siding spring as seen from the surface of Mars. So that's a cool image. Not very detailed in anything. If you want a really good image, unfortunately the missions at Mars did not get the good image. Where are we going to get the good image? We're going to go back to Damian Peach because he gets the coolest pictures, okay? So on the right-hand side, that thing with the spikes that looks like a star, it's not a star, that's Mars. That's how amazingly bright Mars is compared to Comet Siding Spring's lower left of it, okay? So again, just like for Comet Ison, the best comet pictures seem to always come from Damian Peach. He's done. I don't know how he does it. I've never been an amateur astronomer. I've never been a telescopic astronomer or an astrophotographer, but he gets the cool things. All right, so this shows you the correct relative brightness of them. All right, and it also gives you a clue as to what this image is. This is a Hubble image, but it is a composite. Okay, there were way too many people on the internet that thought this was a single image. All right, and if you look at this, okay, go back to this, you can see there's no way you can get Mars in the same exposure anywhere near that you can get the comet. So what Hubble did here is Hubble took separate images of Mars and of the comet, all right, so that it could do the exposure level correctly for each, and then we mosaic them together to show the correct relative scale. Okay, so you can see this is the 20 Mars diameters across, right? All right, but that's the scale of the coma of the comet. And you can see it's not quite big enough to really cause major havoc at Mars. So we had a really, really close approach between two objects in the solar system on the scales of billions of miles. They were coming in, at just hundred-thousands of miles, less than 100,000 miles. But even then, it wasn't enough to cause any major havoc. So it was an interesting event. But nothing, nothing Mars-shattering. How about that? All right. Finally, the coolest image I have seen in years, and I call it "Mind the Gaps." And those of you who've been to London understand what I'm talking about. So, we have for many years been seeing disks of material around newborn stars. Okay, young stars as a cloud of dust material collapses to form a star, it forms a disk around it. And here you can see on the left AU microscopy, where we see the edge-on of the disk, and on the right HD 107146, where we see the face-on to these disks. Okay? And the star in the center, of course, is blocked out by a coronagraph, so you can actually see the disk of material around it. And so we're seeing these disks. And they can be sometimes kind of ratty, but you can see in the top and the bottom here we've got the observation from Hubble, and the bottom is the artist's interpretation to help you guide your eye in terms of seeing these disks around these objects. And so we're finally seeing lots and lots of these disks. We're confirming that star and planet formation goes through a disk. Furthermore, in some places, such as Fomalhaut, we're seeing these rings, and you see this thin ring out here. And this ring at Fomalhaut, okay, was indicative of the idea that planets had formed. One, because it was a nice thin ring, and you need a gravitational body to create that ring. And two, because that ring was slightly off-center, and a gravitational pull of a planet could have pulled it off-center. And so in Fomalhaut, we went in looking, and we found a planet, okay, that potentially could cause it, and we believe that that is the planet that caused the ring there. Now, Hubble has great resolution. Okay, it does amazing things, but there's a new telescope that has just come online. Oops, I'm sorry, I forgot about this other thing. There's one other observation I wanted to do in the setup, is the Keck Observatory. Okay, this is the the disk around Beta Pictoris. The Hubble observation is on the bottom, and the thing up top, you can actually start to see lumps in the disk. Now this is an edge-on disk, and you can see lumps in it where you think that planets might start forming. So we're beginning to see not just the disks and these rings and these lumps within the rings to try and indicate the possibility of planet formation within them, right? But there's a new telescope on the Atacama Desert at 15,000 feet in Chile. And this is a millimeter wave observatory. It's called the Atacama Large Millimeter Array. And with it, they can separate their dishes by up to 15 kilometers. They can synthesize a telescope that's 15 kilometers in length. And this is the artist depiction. And here is a shot of the partially built Atacama Alma up there. And with that, they can start looking at the amazing things. So they looked at a star named H.L. Tauri. Okay, H.L. Tauri, I don't have my laser pointer. Oh, here it is. H.L. Tauri is somewhere in here. This is the Hubble image. All right, you can see the right in there. There is a star H.L. Tauri, and they looked at it in millimeter wavelengths, and they got an absolutely amazing image. Okay, in that small region, they were able to see this. Let me pull it up full size. This is the disk around a 1 million year old star. We can see the gaps and the ring structures and the holes in the ring structures, which are incredibly indicative of the formation of planets in this disk. All right, we have never seen a disk in anywhere near this detail. This is an amazing image. It floored all of us. We were passing it around via email. So many astronomers posted it on Facebook and Google+, all over the place. Just a stunning image. This is the first high-res image release from ALMA when they're out in the 15-kilometer baseline mode where they can get the highest resolution. They will actually look in lower frequencies and able to get even higher resolution than this. It just augurs an incredible wealth of information in millimeter wave astronomy to come from ALMA. And this is literally one of the most amazing images I've seen in years. So we're seeing details of planet formation around other stars. Really cool stuff.
Does lower frequency give you higher resolution? I thought it would be the other way around. I mean, looking.
Maybe I might be flipping that. They're going to look at. How about this? They'll look at other frequencies and get slightly higher resolution than this. How about that? I've been given a teacher workshop for the last 2 hours. I can't think anymore. Okay, so that's the news from the universe, and it's time to move over to our featured speaker. Our speaker tonight is Marc Kamionkowski, who comes to us all the way from across the street at the Johns Hopkins University. Marc got his undergraduate degree at Washington University in St. Louis, then went on to get did his graduate work at the University of Chicago, then went on to Columbia University, where he went to Princeton, the Institute for Advanced Study for a postdoc, and then went up to Columbia, where he gave me half a job. After I finished my postdoc at Princeton, I got half a postdoc at Columbia with Marc and half a postdoc at the American Museum of Natural History with Neil Tyson. So they shared me for a couple of years before I moved on to AMNH fully. So obviously indebted to him for that. Then he went out to Caltech as professor there, and finally came here to Johns Hopkins. He is definitely one of the world's experts in the cosmic microwave background, and really looking forward to hearing from him. Ladies and gentlemen, Dr. Marc Kamionkowski.
So thank you very much. So Frank and I overlapped for a few years at Columbia, and one of the things we did together is try to figure out why galaxies spin. We made some progress. So today I'm going to tell you about something completely different. I'm going to tell you about some new measurements that have been made. The results were announced in March, and we may be seeing a signal from the first trillionth of a trillionth of a trillionth of a second after the Big Bang. Whether we are or not still remains to be determined, and I will try to explain to you the story. So just to begin, there was a press conference at the Harvard-Smithsonian Center for Astrophysics where the team, which is called BICEP2, announced discovery of gravitational waves from the Big Bang. And the Harvard-Smithsonian Center for Astrophysics has these types of press conferences all the time because they're discovering exoplanets all the time, and this is one of the places where they announced the discovery of the exoplanets. The response to this particular news conference, though, was unlike anything they had ever seen before. And in fact, most people who tried to log in to the website to watch the news conference live were unable to do so because there was such demand to watch it that the demand actually brought the Harvard web servers to their knees. So it was really, really huge. It was written up in Scientific American. It was front page on the New York Times, New Scientist. Every single news source in the world covered the story. And in particular, there was, if I can find it here, this Saturday morning afterwards. So let me play it.
Danny, welcome to the show. You're going to start us off with Who's Carl this time. Carl Castle, living legend that he is going to recreate for you 3 quotations from the week's news. Your job, of course, identify or explain just 2 of them. Do that, you'll win our prize. Carl's voice on your home answering machine. You ready to go?
Yes, I am.
All right, here is your first quote.
That's pretty damn cool.
That was a theoretical physicist named Marc Kamionkowski. He's reacting to news that researchers had found evidence of what?
The Big Bang.
Indeed, yes, the Big Bang, or what came right after the Big Bang. Basically, the beginning of the universe. Physicists all over the world were incredibly excited. They said a discovery that was announced this week was the most revolutionary advance in science in decades. It's amazingly cool. It's deeply important. It is impossible to explain in English. They compared the universe to a grapefruit, to a pot of boiling pasta, to bread dough being stretched, and then we realized the physicists had just skipped their lunch. And what happened this week is they announced an experiment that proved that they were right. They predicted this result and they got it. And they said this was such an amazing discovery, so specific, that one person made an analogy to imagine if someone were to create a model of the world in which they predicted that there would be this is their example, a little troll doll under a floorboard on the 3rd floor of Ruth Bader Ginsburg's childhood home, right? That was the example. And then this week's discovery was like somebody going to the home, going to the 3rd floor, opening up a floorboard and finding it. That's how amazing this prediction was. That's the example.
So that would be exciting? Like if I found a...
Anyway, so I am actually going to try to explain it to you in English. And Frank, you're not the only one to screw up my last name, as you can tell here. But that's okay. So that was March 18th, 2014. But it's been over half a year since. And since then, there have been a number of questions raised. So these are some of the headlines. Backlash to Big Bang discovery gathers steam. No evidence for or against gravitational waves. Big Bang discovery comes under fire, etc., etc. So as Carl Sagan said, extraordinary results require extraordinary scrutiny. And these results, if true, are as extraordinary as it gets. And they, therefore, require the most extraordinary scrutiny. So I'm going to give you an update, try to tell you what is going on and what you might want to look forward for in the future. So here's a brief outline. So I'm going to give you some background in about cosmology. I'm then going to tell you about an idea known as inflation that was postulated by a variety of theoretical physicists about 35 years ago. And roughly speaking, it's an idea for what set the Big Bang in motion. I'm then going to tell you how it is that we make measurements of the cosmic microwave background and how it is that we infer all of this information about the early universe from the measurements that we make. And then at the end, I'll explain what BICEP 2 has seen, these gravitational waves. Okay, so I'll explain to you, thank you. So I'll explain to you what BICEP saw, why we believe they may be seeing gravitational waves for inflation, but also the possibility that they might be seeing nothing more than interstellar dust. So there was a NASA satellite that flew in the early 1990s called the Cosmic Background Explorer, which we abbreviate as COBE, and it made a map of this cosmic microwave background. And that map looked like this, and I'll tell you in a few more slides more precisely what it is that we're looking for. But very, very literally, this picture is actually a picture of the afterglow of the Big Bang. This was a very exciting science result. The two principal investigators for the project, George Smoot and John Mather, who's down the road at Goddard Space Flight Center, and who's now the chief scientist for JWST, is that right? Chief scientist, yeah. So they were awarded the 2006 Nobel Prize. So this was a big deal in the world of cosmology and physics. About a decade later, there was another satellite mission flown by NASA called the Wilkinson Microwave Anisotropy Probe, named after David Wilkinson, a physics professor at Princeton University who passed away shortly after the launch, who was responsible for doing a lot of the work, a lot of the groundwork for this measurement. So this is the map that the WMAP satellite made about 10 years ago. And again, this has been an extraordinarily scientifically fruitful measurement or experiment, and I can tell you that the papers that have come out of the WMAP collaboration have been the most highly cited papers in all of science. And in science, citations are our currency. Papers that get lots of citations by other scientists are very, very valuable. And these papers have received more citations than any other science project over the past decade. And I should say that the principal investigator of WMAP is actually Chuck Bennett, who's a professor of physics and astronomy right across the street here. And then more recently, launched in 2009 and taking data since then, the European Space Agency has developed a subsequent generation experiment called the Planck satellite. And this is the image that was first provided by the Planck satellite in March of last year. And again, this was very exciting science, a very exciting science result. It was announced again on the front page of the New York Times and other news sources throughout the world. So this is a picture of the cosmic microwave background as imaged by COBE from the early 1990s. This is an image of the cosmic microwave background as imaged by WMAP. And this is the image of the cosmic microwave background provided by Planck. So you see that every 10 years we've been able to do much better in terms of angular resolution. And angular resolution is good, as you've seen just with that picture of the protoplanetary disk. It's nice to have more information. So here's a picture. Does anybody know what's here? Close. So actually, I gave this talk, I think it might be the projector quality. I gave this talk in Aspen, Colorado, and everybody saw what it was. I've given the talk several other times, and people don't know what it is. So here's a higher resolution image. Okay, but still, that's a pretty blurry image. You know what's going on here. That's the Mona Lisa. And then here's a much higher resolution image. And this is a very pretty picture, and we can infer a lot about the picture by looking at this blurred image. We know that it's the Mona Lisa. We know that it's a picture of a woman, and she's sitting there, and these are her two hands. But this is a much more high-resolution image, and there's a lot more information in here. And if you're an art historian, you would actually go look at the detailed brushstrokes and infer not only something about the general structure of the painting, but you would actually learn a lot about how Da Vinci actually went about making this painting. So the point is that there's a lot more information available when we make high-resolution images. And so now that we have this Planck satellite image of the cosmic microwave background, we have a huge lot more information than we did 20 years ago. So what exactly are we looking at? So now I'm going to attempt to explain to you what it is that this image is showing us. So to do that, I'm first going to show you a picture of the night sky. So this is a picture of the night sky as it appears when you go outside on a clear night and look at it. And you see lots of stars. And when you look with a very powerful telescope like the Hubble telescope, if you see pictures of the Hubble Deep Field, you see lots of galaxies. But the most salient feature of this is not the stars, which are these tiny little dots, but it's actually the black space in between. So most of the sky is dark when you look at it at optical frequencies, which are the electromagnetic frequencies at which your eyes operate. But optical light, or visible light, covers only a very, very narrow range of the entire electromagnetic frequency spectrum. So visible light extends over a very small range of frequencies or wavelengths, and as we go to the left, we're going to longer wavelengths, shorter frequencies. As we go to the right, we're going to higher frequencies and shorter wavelengths. So to slightly higher frequencies than visible light, there's ultraviolet light, which you need to worry about when you go outside, when you go out on the beach. There's infrared light at slightly lower frequencies, which is how these thermometers that you point at your forehead work. There's microwave radiation at even longer wavelengths. This is how you heat up your leftover soup. And the radio waves, which is how we listen to the radio or watch TV. At higher frequencies, there are X-rays. You know what X-rays are useful for. And then at even higher frequencies, there are gamma rays. So there's a broad spectrum of electromagnetic radiation. And when we look at the sky with our eyes, we're seeing only a tiny fraction of what is actually out there. And in particular, if you could look at the sky at microwave frequencies rather than visible frequencies, the night sky would look like this. This is actually a map of the sky as it would appear if your eyes operated at microwave frequencies, and it's actually superimposed on an image of the launch site for a telescope that was flown in the late 1990s called Boomerang, a balloon-borne telescope that flew around Antarctica. So this is actually a mountain in the background, this is actually a cloud, and this is what the night sky would look like if your eyes operate at microwave frequencies. So at microwave frequencies, the night sky is not dark, it glows. This was anticipated not only by theoretical physicists, but also by Van Gogh. And this is a picture of a small fraction of the sky. This is actually our current state-of-the-art image of the microwave sky. So this is actually a map of the entire sky in all directions, and it is called a molewide or equal area projection. So if we took a map of the Earth has a spherical surface. If we were to sort of unwrap it and plot it in this way, then you would see North America over here, South America over here, Eurasia, Africa, Antarctica at the bottom, and Australia over here. So what we look at over here is an image actually of the entire surface of the sky, unwrapped so that we can plot it on this, in this form over here. And what you're seeing with these color contrasts, are regions of hot or brighter or fainter regions that are brighter or fainter, but only by roughly 1 part in 100,000. So to a first approximation, this glow is very, very uniform. But if your eyes operated not only at microwave frequencies, but could detect brightness fluctuations of 1 part in 100,000, you would see that there are some colder regions and some hotter regions. That's what these red and blue spots are. So let me tell you a little bit about cosmology. So cosmology is the study of the origin and evolution of the universe. The first step in this direction is to actually understand something that's a bit smaller and closer to home, the solar system. And so we just heard a bunch of very interesting things that are going on in our exploration of the solar system. We are one of 8 or 9 planets. I don't know what the number of planets this week is. But all of the planets orbit around the sun. And the reason they orbit around the sun is that the sun exerts has a very strong gravitational field that keeps all of these planets in orbit around the sun. It turns out that our sun is a star that's very special to us because it is our star, but in the bigger picture, there's nothing special about the sun. It turns out that it is one of roughly 10 billion such stars, all of which are gravitationally agglomerated into this huge structure that we call a galaxy. And the name of our particular galaxy is the Milky Way. So the Milky Way is a very massive object, and it exerts a gravitational field, and that gravitational field keeps the orbit of each of these stars keeps each of these stars on a roughly circular orbit around the center of the galaxy. And it takes our sun about 200 million years to get all the way around once. So it turns out, though, that this Milky Way is a very special galaxy to us because it is our galaxy. But again, in the bigger picture, there is nothing special about this galaxy. It turns out that it is one of several hundred billion galaxies that we can see in our observable universe. So this is not a picture of the universe. This is actually a simulation, a cosmological simulation. Actually, Frank was one of the pioneers of simulations like this. So each of these little dots here is a galaxy, and this is a picture of a huge volume in the universe that shows how these galaxies are distributed throughout the universe. So the Earth spins around the Sun spins around the Milky Way, and then you might imagine that all these galaxies wind up spinning around each other. It turns out, though, that at this stage the hierarchy ends, as discovered originally by this pipe-smoking gentleman by the name of Edwin Hubble. So Edwin Hubble was an astronomer at Carnegie Observatories in Pasadena, and he made a measurement that revolutionized our understanding of the universe. So those of you who are fans of Isaac Asimov might be interested to pick up a big fat book he wrote called Chronology of the History of Science. And it's a great book, and it starts from ancient times, and it goes through every year and lists the most exciting science discoveries of that year, a collection of years. And he has a very broad and interesting and unique perspective on all of science. And in that book, he calls this discovery, along with the discovery of the double helix structure of the DNA molecule, as the two most revolutionary scientific advances of the 20th century. So what Hubble did is he looked at a bunch of nearby galaxies, and he measured or estimated the distance to each galaxy. And then he also saw that every galaxy was moving away from us. And he measured the velocity with which each galaxy was moving away from us. And what he showed is that there's a correlation. More distant galaxies are moving away from us at larger speeds than closer galaxies. The galaxies that are fairly nearby are moving away from us, but not so rapidly. The ones that are further away are moving away much faster. And from this, we infer that the universe is expanding. And I made a movie. You have to understand, I'm a theoretical physicist. This is very, very high technology for me. So I'm going to show you a movie of an expanding universe. So I want you to look at this pair of galaxies. So each of these red lines is supposed to be a galaxy or pointing to a galaxy. I want you to look at this pair and this pair. So the red pair are closer together, and the blue pair are further away. And now what I'm going to do is blow up the entire grid. And as I blow up the entire grid, what you're supposed to notice is that the blue points are moving away from each other faster than are the red points. So let me play the movie. So there it is. Did you all get that? So the red points are moving away from each other. Whoops. Slightly larger, it's slightly smaller velocities than the blue points. So Edwin Hubble's discovery demonstrated that the universe is expanding. If the universe is expanding today, if all the galaxies are moving away from each other today, that means that at earlier times, if we run this movie backwards, at earlier times, every galaxy would be closer together. All of the galaxies would be much closer together. The density of galaxies would be larger, so the density of the universe, the number of galaxies per some unit volume, would have been larger. So, if this is what the universe looks like today, each of these dots being a galaxy, then at earlier times, the density would have been higher, the galaxies would have been closer together, and at earlier times, the galaxies were even closer together, etc., etc., etc. So one thing that we can do from Hubble's measurement is extrapolate back in time. If we see any two galaxies moving away from each other today, if we run that movie back in time, we can figure out that at some finite time in the past, those galaxies must have been on top of each other. Okay? If I see a car a mile away, and I see that it's driving away at 60 miles per hour, I know that 1 minute ago it was right here. So we do the same calculation with the expansion rate that Hubble measured, and we infer that 13.8 billion years ago, the universe must have been in a state of infinite density. And that is what we refer to as the Big Bang. So this is my picture of an infinite density universe. So I told someone today I'm giving a public lecture this evening. They said, you got to show them nice pictures. They love to see nice pictures. So here's a slightly nicer picture. So this is a picture that illustrates the evolution of the universe as we understand it now. And it's made by the WMAP collaboration. So we live in a universe that's 13.77 billion years old. And we observe it with satellites like the WMAP satellite. And if we look back in time, so as we go from the right to the left, we're looking at further, larger and larger distances. Since light travels at a finite speed, when we look at larger and larger distances, we are seeing objects as they were at earlier and earlier times. So when we look at fairly nearby objects, things like galaxies, we are seeing those galaxies as they were fairly recently. As we go to larger distances, for example, with the Hubble Space Telescope, we can see galaxies that are about 10 billion light years away. We're seeing things that are 10 billion years away, 10 billion light years away. We're seeing them as they were a few billion years after the Big Bang. But even with our most powerful telescopes, there's only a finite distance out to which we can see. With the James Webb Space Telescope, we actually hope to image directly the first stars, which we have very good reason to believe were formed about 400 million years after the Big Bang. But if we look even further back, which we can do with these cosmic microwave background measurements, when we make these cosmic microwave background measurements, we're actually looking at the universe as it was 375,000 years after the Big Bang. And we are looking back a distance of about 13.88 billion light years. Now, the thing that's so exciting about these cosmic microwave background measurements is not only that we're imaging the universe as it was 375,000 years after the Big Bang, but we have very good reason to believe, as I will try to explain in the next few slides, that this image that we have reflects directly what was happening in the very first trillionth of a trillionth of a trillionth of a second after the Big Bang at the time that this process, which we hypothesize, this process called inflation that we hypothesize should have been occurring. So one way of looking at how remarkable this is that when we look at this cosmic microwave background image of the Big Bang, the universe is 380,000 years old. It's now 13.8 billion years old. If you look at a human who is 50 years old, and you try to figure out what fraction of the age must have been, would they have been, when they were 375,000 years divided by 13.8 billion years. This is analogous to taking a picture of a human being a few seconds after conception. And from this image, we can infer the initial conditions that gave rise to everything else later on. So here's another picture of what we're looking at. So this is where we live in the universe. The universe is 13.8 billion years old. Nothing can travel faster than the speed of light, which means that there's a finite distance out to which we see, which we call the horizon. And that distance is 13.8 billion light years. And so when we look at the universe with whatever telescopes or whatever observations we can make, we can only look out to this finite distance. And the cosmic microwave background is actually this surface over here. So when we look at the cosmic microwave background, that WMAP or Planck image is actually a picture of the universe, picture of a spherical surface in the universe of radius 13.8 billion light years, and we're seeing it as it was 380,000 years after the Big Bang. So it's actually a remarkable image. We're actually looking at the edge of the observable universe, and we are imaging it with an amazing precision and resolution. So that's what we're looking at. We're looking at the edge of the observable universe. So what I'm going to try to tell you now is that this picture is not only, amazing because it's the edge of the observable universe, but it's amazing because it provides a huge amount of detailed and precise information about the origin of the universe, its contents, and its evolution. So what I'm going to tell you about in particular is that this picture gives us very good reason to believe that this mechanism that we call inflation actually occurred. that it actually is what set the Big Bang in motion. So as I said, inflation is an idea more or less for what set the Big Bang in motion. What is it that actually made the thing bang in the first place? It's something that would have happened during the first trillionth of a trillionth of a trillionth of a second of the universe. And one of the things that's most exciting, not only to cosmologists and astronomers, but to physicists, is that the mechanism behind inflation is actually based on ideas that come from elementary particle theory. So this is a talk about cosmology. It's at the Space Telescope Science Institute. We're talking about the biggest things in the universe that we see very, very far away. But it turns out that this is actually also a talk about elementary particle theory. So we have a beautiful theory for the physics of subatomic particles. We now know that atomic nuclei are made out of protons and neutrons. We've known this for 80 plus years. We know, moreover, that those protons and neutrons are made out of smaller particles that we call up and down quarks. We also know that those up and down quarks are two of the lightest of 6 quarks. The other 4 are the charm strange top and bottom. All of the chemistry that's responsible for just about everything involved in life and planet Earth, all of the chemistry is due to the behavior of the electrons in atoms that spin around the nuclei. It turns out that the electron is, again, only one of 3 similar particles that we call leptons. It's the lightest, and there are 2 other particles, the mu lepton and the tau lepton. And then associated with each of these 3 leptons are 3 very weakly interacting and very light particles called neutrinos. And we have a theory that explains how these particles interact. These particles interact through the exchange of photons, which is light, but there are also other particles analogous to the photon called gluons and Z and W bosons that also describe the behavior of these particles. And the last piece of this puzzle was discovered just 2 years ago at the Large Hadron Collider, the Higgs boson, and there was a Nobel Prize awarded last year to Higgs and 2 other gentlemen who first predicted the existence of this particle back in the 1960s. So, I am going to try to explain to you why it is that we believe that something like inflation occurred. So why do we believe that something like inflation occurred at the birth of the universe? It's because this map tells us. It doesn't say inflation. There's no I, there's no N, there's no F, no other letters. At some point, some people thought they saw an SH, which stands for Stephen Hawking. I can't see it in here right now, but that has been debunked by the WMAP collaboration. But still, what I'm going to try to explain is that there is a huge amount of information in this map, and it does all but say inflation. So to explain how this works, I took a piece of paper and I drew 100 dots on there. So there are 150 dots, 50 dots. And I put them at random. So you can look at this, and you are not supposed to see any pattern. Okay? I just put 50 dots down. If you see a pattern in there, it's probably just Rorschach. Exactly. So 50 dots at random. So here is another picture, another piece of paper. I put 50 dots on this piece of paper, but there is some structure. And your eye and your brain can process the image that your eye makes, and you can figure it out. So you all see that there are now 5 agglomerations, each that has 10 dots. Okay? So your brain does this calculation. Your brain can process this and see structure in there. Here's another picture. So now there's an additional layer of structure. There are, again, 5 agglomerations of 10 dots, but each of these agglomerations is no longer just random dots thrown out. They're actually more or less circles. Here's another layer of structure. Everyone can see what's different between these two? These are circles. These are squares. So your brain is doing an image processing algorithm. You don't think about it, but your brain is an extremely powerful computer. And then here's another, image, another pattern. So again, this is different, and you can see there are 50 dots. They're not randomly thrown out on the piece of paper, but they're actually arranged in a lattice. So there is information that can be distinguished from seemingly random patterns. And your brain knows how to do that. Not only your brain knows how to do this, but your computer also knows how to do this. So any of you have an Apple and use iPhoto. There's this new feature that came out a few years called Faces. And the computer will actually go through all of your pictures and guess with pretty good accuracy who the people in those pictures are. Okay? So computer scientists have actually developed in recent years very powerful algorithms for facial recognition. So again, the computer can now do something like what you do. You look at two people. No two people look alike. You can always tell any two people apart. In the computer, we've now been able to train the computer to do the same thing. So this looks like gibberish if you don't know how to look at it. This is some more gibberish. So can anybody read this? This actually says something. So interestingly enough, I gave a talk to high school physics teachers from the area over the summer, and several of them actually were able to read this. So this is the simplest possible code. This is, I think, called the one-letter swap. So if I take this sentence and I replace every letter by the preceding letter in the alphabet, so I replace every B by an A, every C by a B, every D by a C, then this winds up saying the true sign of intelligence is not knowledge but imagination, which is something Albert Einstein said. So the point is that what you see and what initially appears as gibberish can actually have meaning if you know how to crack the code. And this is actually what we do in science. The point of science is to find hidden patterns in nature. Here's another example, not from code breaking, but from science. In paleontology, you find a bunch of rocks or fossils. And then, if you know what you're doing, you can assemble them. It's a puzzle. You put it together, and this bunch of random rocks actually turns out to be a dinosaur. So this is not gibberish. And the way that we actually crack the code, the way we actually interpret this image, is to employ mathematical techniques that were developed by Joseph Fourier in the early 1800s. And what Fourier showed mathematically is that any pattern can be represented as a bunch of waves. Anything can be represented as a bunch of waves. Those of you who read about the particle-wave duality in quantum mechanics, the particle-wave duality is nothing more than the observation that Fourier made in the early 1800s that anything can be represented as a bunch of waves. This laser pointer can be represented as a bunch of waves. And when you learn about Fourier analysis in mathematics classes, it's very, very straightforward. So it turns out that you can just apply what we call a Fourier transform or a wave transform to this map. And when you apply a wave transform to this map, it winds up looking like this. And this has structure that you can see. And to the trained eye, it's not just structure, but it's actually beautiful and has a huge amount of information. This, which is mathematically equivalent to this, this is the fingerprint of inflation. So it turns out that what's particularly interesting is not just that we can make the image, so seeing this image tells us that something like inflation must have occurred in the early universe, but moreover, there's a lot of information. So there's the radii of the rings, there's the width of the rings, for example, there's the brightness of the rings. So this ring, this dot is a lot brighter than this ring over here, this ring is brighter than this one over here. There are also these troughs. They're dark, but not necessarily completely dark. And then there's the width of the rings. How wide is this one, et cetera, et cetera. So there's a lot of information in here. There are a lot of numbers that I would need to fully describe this pattern. And if we process this information a bit further, what we infer from this processing is that the atoms of which we are composed, of which everything in the solar system is composed, constitute only 4.6% of the energy density of the universe. There is something called dark matter, which holds galaxies together, which makes up 23% of the universe. And then there's dark energy, which makes up the other 72% of the universe. And this was discovered in 1998, and Nobel Prize was given to 3 gentlemen, including Adam Rees across the street, for this discovery back in 2011. The other thing this image tells us, as I told you, is that something like inflation must have occurred. So we live in a universe that's 13.8 billion years old. The first stars were formed 400 million years after the Big Bang. We have this very nice image of the universe as it was 380,000 years after the Big Bang. But that processing of that image, that wave transform, that fingerprint, tells us that something like inflation occurred in the first fraction of a fraction of a fraction of a second after the Big Bang. So we can feel very proud of ourselves because now we have a very elegant model for what happened, what set the Big Bang in motion. But that's never enough for scientists, and we want to know, what else can we learn? Can we characterize this period of inflation any better? And the answer is yes. So it turns out that inflation makes a number of predictions, some of which were verified with this fingerprint that we saw in the cosmic microwave background. But inflation also predicts that the universe should be filled with a gas of gravitational waves. So electromagnetic waves are light. And the way electromagnetic waves work is as follows. So think about a radio transmitter and a radio receiver. There is an antenna at for the transmitter. You can see those antenna towers on Antenna Hill across the highway. So those antennas have metal. And what happens is they set up electronics so that the electrons in that metal shake up and down. Those electrons have an electric field. And when those electrons wiggle up and down, they send out a propagating disturbance in the electromagnetic field. And that wave travels to the antenna in your car. And the antenna in your car has a bunch of free electrons. And what happens is this wave comes along, it hits these electrons, and it sets those electrons in motion, and then your radio processes that signal and plays top 40 hits or whatever else. So that's how electromagnetic waves work. If I set electric charges in motion, it sends out waves, and then those waves set other electric charges in motion, and that's how we use these for communication. It turns out that in gravity, there is something similar. If I take a massive object that has a gravitational field, like the sun has a gravitational field, if I were to shake the sun up and down, that would give rise to a propagating disturbance in the gravitational field. And then if there was some other test mass, like a planet far away, that planet would get set in motion. So this is a picture of what would happen if a gravitational wave hit a spherical object. What a gravitational wave actually does is not shake the object up and down as it does with an electron, but it actually gives rise to distortions in the shape of this spherical object. It elongates it in this direction, and then it elongates in this direction, this direction, etc. So it would take an object and sort of make it wobble around, its shape wobble around. So inflation predicts that the universe should be filled with these gravitational waves, and in particular, those gravitational waves would hit the cosmic microwave background surface of last scatter. So remember, when we look at the cosmic microwave background, we're looking at a spherical surface at the edge of the universe, at the edge of the observable universe. In the absence of a gravitational wave, that surface is perfectly spherical. But if these inflationary gravitational waves exist, they would distort the shape of that surface of last scatter in some particular way. So what my colleagues and I and another group realized in 1996 is that the gravitational waves produced by inflation give rise to a signature in the polarization of the cosmic microwave background. So it turns out that light has properties that are apparent to all of us. Light can be brighter or fainter. Some things are very bright and some things are very faint. Light also has color. It can be red, green, blue, etc. It turns out that there's another property the light has that our eyes are not really tuned to detect, and that is polarization. So remember, an electromagnetic wave is a wave. So if I shake an electron up and down, the electromagnetic wave is going to go like this, run into you. And if you have an antenna that's pointed in this direction, then the electrons will shake up and down. But if I have an antenna that's pointed in this direction, the electrons can't shake up and down. There's nowhere for them to go. So if I have an antenna that's oriented this way, I can tell whether the electromagnetic wave is coming this way. And if I have an antenna oriented this way, I can detect electromagnetic waves where the shaking is in the horizontal direction. And you can actually detect this. If you have polarized sunglasses, next time you go to the ATM machine, most ATM machines are LCD screens. Most LCD screens are polarized. If you take your polarized sunglasses and rotate them by 45 degrees, the screen will disappear. So light is polarized, and you can measure it. It's easy to detect polarization. So here's actually a picture of what I told you before. Electromagnetic waves are, Electromagnetic waves are what we call transverse waves. They shake up and down, or side to side. And this is in distinction to longitudinal waves, like sound waves. So when I talk, there's a sound wave that propagates, and it actually has a wave that compresses along the direction of which it's propagating. Anyway, electromagnetic waves are transverse waves, and so they can have this linear polarization that's either up and down or side to side. So now suppose I look at an image. There's a polarization over here, there's a polarization over here, a polarization over here. There could be a polarization at every point. So here is an image, a polarized pattern that I can draw on the surface of the board. And here's another polarization pattern that I can draw. And here's another polarization pattern. Here's another polarization pattern. The difference between the ones on the left and the ones on the right is that the ones on the right have a handedness. This one swirls around in a counterclockwise direction, and this swirls around in a clockwise direction. If I were to look at this in a mirror, it would look like this, and vice versa. If I were to look at this in a mirror, it would look the same. If I were to look at this in a mirror, it would look the same. So these we call in technical jargon E modes, and these we call in technical jargon B modes. So the B modes have the swirling pattern. And what we realized back in 1996 is that gravitational waves give rise to the swirling pattern in the CMB polarization. So this is something that we pointed out in 1996, and various other theoretical physicists studied it and found it interesting, and experimental physicists also thought that it might be interesting to try to measure, look for a swirling pattern in the polarization of the cosmic microwave background. So since then, there have been a huge number of independent experimental groups that have been looking for this. So this ABS stands for a B-mode search. This is a Princeton-led collaboration. Lightbird is a Japanese project that's on the drawing board. EBEX was a University of Minnesota-led balloon experiment that flew recently. The Atacama Cosmology Telescope is a Princeton-led collaboration in Chile. The Polar Bear Simons Array is, I believe, also in, actually I don't know where it is, I forget. I think it's also in Chile. This is a UCSD, UC Berkeley-led collaboration. The Planck satellite was not designed to make these measurements, but they did a last-minute change to the design to measure polarization. Piper's a NASA Goddard Space Flight Center effort. LSPE is a Rome, a project, an Italian project. SPIDER is a project led by Princeton University. SPT-POL is this huge collaboration led by University of Chicago. And then there's also a project right across the street called the CLASS Telescope led by Chuck Bennett and Toby Marriage that's also looking for the signal. So this is a big deal, and a lot of experimental groups have been racing to detect this swirling pattern in the CMB polarization. So that's why there was a lot of attention given to this announcement on the 17th of March, 2014, of detection of the swirling pattern. So this is actually the map of the cosmic microwave background polarization that this collaboration made, that this telescope made, and you can see the swirling pattern. So around this red spot, the polarization is swirling in this direction, and around this blue spot over here, it's sort of swirling in the other direction. So this, if it is what they believe it, if it's what they claim it is, what they think it is amazing. So, the question now is whether they are really seeing a B-mode signal from gravitational waves from inflation, or possibly just some contamination from dust in the Milky Way. So when we look at this cosmic microwave background, we have to look through our own galaxy. And it turns out that our own galaxy has a lot of interstellar dust. And this interstellar dust can emit light that can be polarized. And so we're not really sure whether what they're seeing is gravitational waves or dust. So back in March, BICEP2 actually provided several fairly persuasive arguments that their data does not look like what we would expect dust to look like. But other people since then have said, well, we don't really know what dust looks like. Interstellar dust is very complicated. Anybody who's trying to sweep up a floor knows that dust can be very, very complicated. And more recently, back in September, the Planck satellite released new data on dust that actually seems to indicate that dust does not look like what BICEP2 thought it should look like back in March. So we don't really know now whether that signal, that B-mode signal that they detected, is gravitational waves or dust. So what we're trying to do now is figure it out. And one way that we're hoping to figure it out is through frequency dependence. So I told you that light has electromagnetic frequency. There are a broad range of electromagnetic frequencies. It turns out that the B-mode signal that they are looking for would be very large at roughly 150 gigahertz, the electromagnetic frequency at which the BICEP2 measurements are made, but smaller at higher frequencies and smaller at lower frequencies. Dust, on the other hand, would be much larger at higher frequencies than at lower frequencies. So what BICEP did, in order to try to distinguish whether they were looking at the cosmic microwave background or dust, was use data from 150 gigahertz and weaker data, lower signal-to-noise data from 100 gigahertz, complemented by not very precise information from WMAP at low frequencies and not very precise information from Planck at higher frequencies. So the idea that the algorithms they used were good algorithms, but the data available were not very, very good. So what my colleagues across the street, Chuck Bennett and Toby Marriage, are trying to do with this CLASS telescope, Cosmology Large Angular Scale Surveyor, is to try to do this multi-frequency measurement more precisely. So here's another picture of this along the lines I showed you. So the signal strength for gravitational waves from in the cosmic microwave background looks like this, whereas the signal from the galaxy goes down and then back up. And they actually hope to image the sky in 4 frequencies, 40, 90, 150, and 220 gigahertz. And if they can measure the relative strength of the signals in these 4 different frequencies, they can distinguish the contribution from the Milky Way from the cosmic signal that we're really interested in. The other thing that we hope to do is try to use the spatial dependence of the signal, roughly a cross-correlation. So Planck provides a map of the dust. It tells us where the dust is. And then we can look at the BICEP2 signal and see whether their B-mode amplitude is bigger, where Planck tells us the dust is. And it is very, very literally like trying to match fingerprints. So we have a fingerprint of dust from Planck, and this is what BICEP2 might look like. And we want to know whether this fingerprint looks the same as this fingerprint. So the question is, when we actually image the dust map, which is being provided by the Planck satellite, will it look more like this or like this? And the answer is, we don't know. The measurements have not been made yet with sufficient precision, but we hope that they will in the next few years. So the next steps are to overlay the Planck and the BICEP2 maps to see whether they look the same or not. If they look completely different, that provides some reasonable evidence that BICEP2 is seeing gravitational waves. If they look the same, then BICEP2 is probably just seeing dust. In science, things are not true because somebody or some collaboration says they're true. They're true because many different scientists make independent observations and come to the same conclusions. And so there are all these other competing telescopes which are catching up to BICEP 2 in terms of sensitivity. And if BICEP 2 is seeing gravitational waves, these other guys should be seeing them too. There's the frequency dependence that I talked about. And then if there is a gravitational wave signal, it should be the same all over the sky. Whereas the dust signal is brighter in certain regions of the sky than in other regions of the sky. So I am a theoretical physicist. My job is to make predictions. And so I am going to make a prediction. My prediction is that we will figure it out. But this is very exciting. So, back in early summer when I agreed to give this talk, I thought, this is going to be the victory tour talk. We discover gravitational waves. Someone's going to get a Nobel Prize, and this is great. And we'll be, talking about this decades from now. But I don't know. So I have to say that the arguments that BICEP 2 gave that it's not dust were very, very convincing at the time. And there's still many intriguing things about the data that suggest that it's not obviously dust. But it is true that since then we've realized that dust is more complicated than we thought back in March. So we really don't know. I do think there's some good reason to believe that we may, at the end of the day, be seeing gravitational waves, but I don't know yet. If these are indeed gravitational waves, it's as exciting as it gets. We're seeing some possible consequences of the unification of the fundamental forces at energy scales much greater than those accessible with laboratory experiments. This would constitute the first detection of gravitational waves. I did not mention this, but these gravitational waves are produced by a Hawking-like process in the early universe. So it would actually be discovery of Hawking radiation. The physics that produces this, in some sense, merges gravity and quantum mechanics, or at least scratches the surface of a merger of gravity and quantum mechanics. And the biggest thing that theoretical physicists have been trying to do in 20th century and 21st century science is merge general relativity, Einstein's general relativity, with the laws of quantum mechanics. And if this is what we think it is, this is actually scratching the surface of what may ultimately prove to be a merger between gravity and quantum mechanics. And perhaps most exciting is that if this is what we think it is, if it turns out to really be inflationary gravitational waves, then we are actually seeing a brand new signal from a trillionth of a trillionth of a trillionth of a second after the Big Bang. And if they've detected are these B modes from inflation, then what we've only discovered so far is a Rosetta Stone. And it took many years after the discovery of the Rosetta Stone to actually crack the code and figure out what's written there. And over the next few decades, if these are B modes, we can measure these B modes more precisely through the same types of analyses that we've done on the cosmic microwave background maps we have so far. And we have an entirely new avenue to study what happened very first microsecond after the Big Bang. So I will close by saying stay tuned. Thank you.
Okay, so you all get all of that? Okay. Complex field, lots of cool things. I'm sure there are a few questions. How about you, right there?
The microwave radiation subject to gravitational bending. I mean, it's going past every object in the universe. So
Yeah.
Is that affecting?
Excellent
Mark,
question.
could you repeat the question
Yeah.
for the webcasting audience?
So the question is whether the cosmic microwave background is affected by gravitational lensing. So this cosmic microwave background comes from a very large distance. So this light, is emitted from the cosmic microwave background surface of last scatter. It goes a very, very long way before we see it in our telescope. And it passes by a lot of things, a lot of galaxies and clusters of galaxies. And we know that general relativity bends the trajectories of light rays. So you might ask whether that cosmic microwave background image is distorted by this gravitational lensing. And it turns out that it is. And this was one of the big results of the Planck satellite last March of 2013. Now, I don't have the image with me. They actually have measured the distribution of mass in the universe by the effects of by the gravitational lensing distortions of the cosmic microwave background. So the answer is yes, and it's one of the major triumphs of the Planck satellite.
Okay, other questions?
What is dust? What's it made of? What scale? Is it carved up?
So there are different ideas about what it is. Most of it is probably silicates, and these dust particles have a wide variety of sizes, but a micron is a typical size. So like they're much smaller than sand particles. I think if you take two erasers filled with chalk and bang them, I think that those chalk dust particles are comparable in size. So it is
Density, how
dust.
many per cubic meter?
It's tens of grams per centimeter cubed. It's like sand. So very small. We don't know what it is in detail. There are various ideas. And then it also merges into things called PAH molecules. So a very small dust particle winds up looking like a very big molecule. But basically it's, dust, like, chalkboard dust.
Could gravitational waves turn out to be some source of humongous amounts of energy that we could tap into?
No.
Repeat the question.
So the question is whether the gravitational waves might turn out to be a huge source of energy density that we could tap into. So the answer is no. So there are upper limits to the energy density of these gravitational waves, and the best upper limit is that it's 1/10 of the energy density in the cosmic microwave background. And that's a very small energy density. So the roughly 400 photons per cubic centimeter. And they're very long wavelengths, so very low energy photons. The more difficult part is the tap into question. Detecting a gravitational wave is extremely difficult. The motions that these gravitational waves would induce in test masses is extremely feeble. And just the idea of getting energy from waves is tricky. So Tesla had this idea. So Tesla was a genius, but he was also a semi-nut. He had this idea that we could do energy transmission not by laying cables, but by propagating radio waves. And it didn't work, and he blew up several things trying to. Electromagnetic waves are 40 orders of magnitude stronger than gravitational waves. So if we can't do with electromagnetic waves, it's not going to.
Say 40 orders of magnitude?
Just a bit. Over here.
This is a sort of follow-up to the first question. How do we know that sort of the image of the microwave pattern measured by Kobe and the subsequent satellites has not been distorted by other intervening sources of microwave or factors?
So it turns out that the predictions of inflation for the cosmic microwave background pattern are very, very precise. And the prediction is that the image should be what we call a Gaussian random map. So it's a very, very specific prediction. So you know what a bell curve is, right? Bell curve goes up and it goes down. It has a very precise mathematical description. Anything else is not a bell curve. So if I draw a curve that goes like that, that's not a bell curve. If I draw a triangle, that's not a bell curve. A square is not a bell curve. Anything that's not a bell curve is not a bell curve. And anything that's not a Gaussian random map is not a Gaussian random map. And it turns out that the images are Gaussian to 1 part in 10,000. So we know that the distortions are extremely small. But we now can detect these very tiny distortions, and those very tiny distortions we can attribute very precisely to the effects of gravitational lensing.
Okay, in the back there.
Just a simple question, but on the B modes, would that create bumps on the outside edges? Maybe I'm saying it simply, but the outside edges of where you have inflation. You had one picture where there was like kind of a ball with spirals. Will those B modes actually rotate and create like dimples on the outside edge, or how does that work?
It's the other way around. So what happens is that there's surface of last scatter.
Yeah.
So the photons, the light that we see in the cosmic microwave background is actually emitted from the surface of last scatter. And what happens is that gravitational wave comes in and starts jiggling, starts moving it around. And those motions are what gives rise to the polarization pattern. So it's the motions induced by the gravitational waves give rise to that polarization pattern not vice versa, if that answers the question.
No, I got that. I was just asking, will that, is there varying density or something that's creating that, and is it a flat wall on the outside edge of that, or is it something that energy goes both directions, or is it only coming one way?
Oh, I see. It's going in all directions, but we only see the stuff that's coming towards us.
Right.
Okay. Question here?
In this, the Kobe and WMAP and Planck background radiation, you mentioned hotter and colder. Is that a spectral or an intensity, or is it the same difference?
What does hotter and colder mean?
So hotter and colder means brighter. What I should have said is brighter and fainter.
So it's an intensity measurement, or is it or is it a difference in frequency, wavelength?
It's an intensity measurement.
Okay.
And I can tell you more if you want more detailed information about what precisely they're measuring. But it's an intensity measurement.
Okay, way in the back corner there.
Okay, if a car is going away from me, I can see their lights because the speed of light is faster than the rate of that car. And you just said we can't see things going away from us. So you're saying all the galaxies are moving faster than the speed of light, so we can't see things moving away from us?
Oh, so
that's the first question. The second question is, if we're moving in this direction and everything's expanding, we should be looking this way and not see anything. But if we look back the other way, we should see, things coming towards us, unless things should be a little bit more denser. So now that you've told me about the Big Bang, it makes me think that whatever that source is over there is not one Big Bang. It makes it seem like it's a series of bangs, so that additional matter would be released from that source. Like, peeling an onion. An onion has layers, and one layer bangs, and then the next layer bangs, the next layer, so that when we look that way, we don't see anything. But when we look back, we can still see matter and stuff coming towards us.
okay, so the understanding the Big Bang is probably it's the hardest thing to explain and to understand. And I had to take general relativity and cosmology several times before I really understood, I think. So when we think of explosions, so the Big Bang is often described as an explosion, but it's kind of a misnomer, because when we think of explosions, we think of something over there blowing up, and then we see it. But that's not the Big Bang. What we observe is that the entire universe is expanding. Imagine that I had a balloon that was very small, and I blew it up slowly. And think about the surface, which is a two-dimensional universe. Every point on that universe is moving away from every other point. Every point on the surface of the balloon is moving away from every other point as I blow it up. But there is no place on the balloon that's different than any other place. And the expanding universe is a three-dimensional analog of the surface of a balloon that's being blown up.
Period.
Okay. Yes,
that's the answer.
Let me just underscore that the expansion of space.
Because there could be other balloons inside, and if you're looking at the surface of another balloon inside of that balloon, and they're all expanding.
Yeah, we can't do that. So the problem with this analogy is that when we look at the balloon, it's a two-dimensional surface that we can see because we're in 3 dimensions. And for this analogy to work really well, we would have to live in 4 dimensions and be able to look at our 3-dimensional universe from outside it. We can talk afterwards. I can try to explain more.
Yeah, the expansion of space as being the stretching of space and not really motion through space is one of the fundamental pieces that you have to grasp in order for some of this to make sense. All right, we have hit at 9:30 and I always like to cut off 9:30 so everyone gets home at a good amount of time. Next month, December, we will have Joshua Peak on outer space. The landing on the Rosetta on Comet Rubber Ducky, Churyumov Gerasimenko, is like, what did we figure out? It was 11 a.m. tomorrow or something like that, Eastern time. And somebody put up here that Adam Reese is getting yet another prize. And it's going to be simulcast on the Discovery Channel and Science Channel, 6 p.m. Saturday, hosted by Seth MacFarlane and other things like that. So, if you want to see yet another thing for Adam Reese, go ahead. All right, thank you all for coming. Let's give Mark another hand.